Thanks for being here. As you know, the topic is about attacking VPNs. Really excited. This is my third black hat. This is the third black hat I'm speaking, and this is the first time I'm talking something related to crypto. I'm more of a web app sec related guy. I'm really nervous when I see crypto related stuff. So. And during some of my recent work, I was able to come up with this stuff, and I'm so happy to be here. So let me try and give you a little bit background about myself. I call myself Nafeez, and I've been building this product called Asset Watch over the last few months. It's basically a transparent attack surface discovery service. If you have any questions, please feel free to contact me on Twitter, skeptic_fx. All right, so let's see what are the topics that we are going to cover today. A little bit about compression side channels and encryption. I want to cover a broader audience. So if you're someone who's very new to compression Oracle side channel attacks, I'd like to go through what they are, how they are relevant, and the history of attacks around compression Oracle so far. And the end goal here today is I'm going to take a VPN and leak secrets from it. So it's a generic attack, but I'm going to show a specific demo on a very specific VPN called OpenVPN, which some of you might have heard of, which is used popularly, right? And obviously, I will also go ahead and say what's the way forward, how to defend, things like that. So let's get started. So compression, data compression is a very important topic in networks and any application. Ultimately, you want to send data at a much lesser bytes on the wire. So there are a couple of methods of doing data compression. One of them is the LZ77 families of compressions called the LZO or the LZ4. You might have heard of it. So what it does is just try and look for redundant patterns and try and see if it can replace existing patterns with shortcodes. For instance, in this sentence, as you see, everything looked dark and bleak, everything looked gloomy. You already see this pattern, everything looked and everything. So what a compression algorithm does is try to not repeat the word everything looked. Instead, it replaces with something like -34 and 18, which says, hey, so what you have to do now is go back 34 bytes and repeat the next 18 bytes from there. And now when you look at English sentences in general or things that are very good for compression, this works really well. And it's very much used in most of the things that you do compression in computer science. And the other one is, again, pretty famous one. Most of you might have heard of it, the Huffman coding. So the LZ77 family does what is known as at the byte level. It tries to look at bytes, but the Huffman coding looks at bits. So if you have redundant bytes, for instance, space or the letter T, which happens to repeat more often, then what the Huffman coding does is try and use those characters as a frequency and tries to substitute them with fewer bytes. So in this case, this will be like some 3 bytes. So, you kind of get some efficiency over there. Enough data compression. If you tie these two algorithms together, you get something called as a deflate, which is very famous and used in zlib, gzib, all these compression algorithms. So if you know TLS compression, which has been around for around a decade, very notorious for compression Oracle attacks, they have been using deflate, and your zip files and compressing files, most of them use these kind of algorithms. All right. With that being said, we understand what compression is and how it works. Let's try and understand what is a compression side channel. So around 2002, this gentleman called John Kelsey, he came up with this amazing paper, a very theoretical paper on how compression can act as a side channel in cryptography. So what that means is that if all of us know that today, any encrypted data is, its length is more or less leaked. You can always, if there is an encrypted data of 50 bytes, you know that is 50 bytes. The length is always leaked. There's not very easy way to hide them. And as an attacker, you can always look at them for any network traffic, be it VPNs or be it SSL channel, TLS channel. Now, the whole understanding of this attack that he's trying to talk about theoretically is that, imagine you have a black box. Sorry, I put the white box because I've been using a completely black screen. So imagine this is the black box which does a compression followed by encryption. And you feed in some plain text data and it follows by, and you get back some encrypted data. Now, what happens if there is an attacker who can add his own set of bytes to the plain text data? He still cannot see the plain text data, but let's assume that he's able to inject some plain text data. And if he's able to also observe the traffic length, which means a normal MITM. So if these two conditions are met, then you can effectively have what is known as a compression oracle attack, right? I know it's still theoretical. I'm not talking anything about how this works in real world. So effectively, a compression oracle attack is a chosen plain text attack. In cryptography terms, this is kind of like a brute force attack, where you try to brute force a secret that you are interested in as an attacker, byte by byte, instead of trying to guess the secrets all at one time. So if, let's say, your secret is 5 bytes, you try and a compression oracle attack or any kind of an oracle attack allows you to decode the secret byte by byte. So you don't have, it gives you an exponential level of performance. Instead of repeating 10,000 requests, maybe you just need to have 100 requests at the maximum. So going back to the diagram that I just showed, I'm just trying to fill up this with some more text. So in this case, the one at the very top is the application data. So if there's an application that is trying to encrypt something, this is the data that it's going to give it to the encryption algorithm. Now, assume the attacker can also inject something into it, just like I said. So here in this case, it's secret equals 1. Now, you can see just before that it goes to the black box, the whole text looks something like this. So if you take a closer look about what the attacker injected and the whole piece of text, there is a pattern here, right? So the ones in the green, it looks like it can be compressed. So here, the attacker knows the application uses a secret, and it has a prefix called secret equals. So you can imagine in real world some things like cookies. So cookies have a cookie name and a value. So regardless of the instances of that application, the cookie name would remain the same, just the value changes. So as an attacker, you're interested in finding out just the secret. All right. So let's see what the attacker does here. So he tries to send secret equals 1, and he observes the length as 30. Now he tries it with 2, now with 3, 4, and he tries it with 5. And when he sends 6, what happens is the compression length increases. So instead of compressing in the previous case with 5, where the green text that you can see here is just from secret till the equals part, but the moment he sends a 6 instead of a 5, the window increases, which means effectively the length of the total payload decreases. So I believe that should give you a very good understanding of what compression oracle attacks are. And I spend a little time here trying to understand that. So, all right. Now so that's all theoretical. This is what the paper talked about in 2002, and people didn't come up with anything interesting in terms of real world attacks unless, till browsers emerged and, the cross-browser mashup features came up. So about a decade later, that means 6 years back, a couple of guys came up with something very interesting. I'll go to that. So here, to do that, you need certain properties to do these two things in a real-world browser, which is the observing encrypted traffic part is quite easy. It's happening all the time. Your ISP or government, or if you're in a Wi-Fi in the same network, you can observe traffic of others. MITM is straightforward. However, trying to do the injection of the attacker's part was not well known. So what happened was you could actually use browsers to send cross-domain requests, and browsers have this property called ambient authority, which is their cookies are sent regardless of where you send the request from. So if you send a request from a.com to b.com, a.com will still have, the b.com request will have its own cookies, which the browser attaches as part of its ambient authority nature. It takes it from the cookie jar and attaches it. Now, as someone who can send a cross-domain request, you can add your own bytes to it. So in 2012, Giuliano and Tai Dong came up with this very famous attack called CRIME. You must have heard of it, which basically translates to compression oracle. CRIME refers to, does anyone know what CRIME stands for? It just doesn't come to my mind, sorry. Compression ratio info leak made easy, right? So they came up with real world exploits on GitHub, I believe, and PayPal. They were able to leak the cookies of all these websites over HTTPS. Basically, CRIME means compression oracle attacks on TLS compression. So the one that I just said, which uses deflate. So after this, TLS compression completely died because compressing and then encrypting is bad. The interesting thing about their research was that they were able to predict the future attacks that would come based on CRIME. So one of the things that they clearly mentioned was HTTP GZIP can be a problem, which means not just request cookies, but also HTTP responses can be attacked. So you have interesting artifacts like CSRF tokens and a few other things in HTTP responses that can be attacked as well. So eventually, in 2013 Black Hat, there was this attack called Time, where you had exactly what they talked about, HTTP responses. And one of the interesting things that they introduced was how to do this purely from browsers. So instead of using a man in the middle, they were able to do this purely using a browser, using side channels in the browser itself. Things like TCP window timings and measuring the time measuring how long does the packet size takes. And later on, you might have heard of this breach attack, which got a lot of press attention, in my opinion, more than Time did. But what breach was trying to do was effectively Time, but much more practical. And they were able to leak CSRF tokens of real-world web applications. And in a real world today, if it's a previous generation web application which doesn't use APIs, which the cross-domain security is fully on CSRF tokens, then it's as good as leaking the cookies. So far, we have been seeing enormous amount of attacks on TLS using compression oracle attacks, and a lot of improvements, especially Heast attack was very famous as well, along with one of the recent talks called Practical Developments to Breach. So what I've observed is that people have done as much research that's possible with respect to TLS. So what's new today, right? So obviously, we are going to talk about VPN tunnels. So can we change the whole direction and try and look at VPN tunnels as a completely different transport? So one of there are different kinds of VPNs. Those are out there, the TLS VPNs, which is of interest today, and then there's IPsec and the ones that generally used in the corporates. So I'm going to focus more on TLS VPNs. What I mean is things like these. These are modern day SaaS-based VPNs, which you can just, as a normal user, can go and sign up and get your free account or a monthly account for like $10 per month. And all it allows you to do is just connect to different services through their VPN. And it is supposed to protect you from data integrity, and data, make sure that your data is not leaked on the internet. So what are these VPNs commonly made of? So if you really look into and understand most of these SaaS VPNs, TLS VPNs that are out there today, they are completely based on an OpenVPN. Not all of them, but most of them, they just take OpenVPN, which is an open standard, and it's an open source project. So they just have a ready-made VPN client and server implemented. So that makes their job easier. All they have to do is just implement them and make it a SaaS service. Right. So let's try and look at OpenVPN's high-level overview, which is basically just like TLS. They have a control channel and a data channel. So in the control channel, they negotiate what to do, which is in fact just like what TLS does. In fact, they use TLS within themselves, and they extensively use the OpenSSL library as well, the OpenVPN code. And if your control channel agrees that we should do compression, then all the data that is going to be encrypted is going to be compressed. So when I say all the data, I mean everything. Even if it's a UDP packet that's going to go out, or a TCP, or even any layer of packet is going to be compressed. And the interesting thing is both the client and the server does it. So you kind of get bidirectional. So if your target under attack is HTTP, you get compression on requests as well as responses, right? So yeah, I started looking into OpenVPN. So I had this understanding of, okay, compression Oracle attacks can work on VPNs. And I was thinking, let's try and see what OpenVPN does, and can we come up with a real-world exploit on OpenVPN. So I started looking into their algorithms. So they use a simple LZO, LZ4, which is very performant, and in my opinion, simpler than deflate, which complicates it with Huffman coding. So in my opinion, that's easier, even in terms of development and even in terms of from an attacker's point of view, because with Huffman coding, there are other complex issues that's part of doing a compression Oracle attack. And so yeah, as I said, with respect to VPNs, we have a complete data channel compression followed by encryption. So what we can do is the attack that I'm going to talk about today. So I would like to name my attack Oracle. It's basically a combination of VPN plus Oracle. And one of my favorite bands used to be this guy called Oracle, so I just went with it. I've been seeing all these attacks, and I think I did some justice by at least not creating a logo and a website for that. So yeah. Okay, so what does Oracle attack say? Any VPN under a HTTP web app. So if you have a VPN and you're using pure HTTP web apps, then everything under that, secrets under that can be leaked bidirectional. So if it's HTTP requests, you can leak cookies. If it's HTTP responses, you can leak CSR tokens. So just want to make things clear. This part makes this attack less interesting, and that's obviously so, because if what your VPN gets is a HTTPS traffic, it is not going to do anything more with it. Even if it tries to compress, because it already has an encrypted data in hand, the entropy is too high, compression doesn't make sense. And even if it compresses or doesn't compress, it doesn't make a difference, because it is not compressing what the attacker provided. So everything that's TLS or encrypted is already safe. So that also includes SSH. However, things are different, as I said, for insecure protocols. So HTTP, DNS, usual corporate stuff behind a VPN, all these can be attacked. So in this talk, I'm going to specifically look into how we can leak secrets from a HTTP website through a VPN tunnel. All right? So let's talk about the requirements here. As an attacker, you want your VPN server and client to use compression. And if it's enabled by default, that's great. And as usual in a regular MITM attack, you want to observe the length as well, which is possible. And yeah, like the beast crime style attacks, you want the victim to visit your attacker website. So in this case, attacker.com injects your malicious JavaScript, which steals the data. So let's look at the setup to explain it more in an infographic way. So you have a VPN user using a browser here. and who's trying to access his, let's say, corporate website, which is over HTTP. By default, he wouldn't do that because it's plain HTTP, and for some reason his server didn't upgrade to HTTPS. I don't know, because they don't want to get a free Let's Encrypt certificate. So they use a trusted VPN provided by their corporate or the ones that they want to use. And in this case, they are protected. However, if you have an attacker who can conduct a Oracle attack here, they would have an attacker.com, which they can host the injected script, as I said, and they can already, we can assume that he can look passive MITM, and he can inject ads through the website. So the first part is obvious. With the MITM, I can observe, the attacker, I can observe the length, and the second part is where I use to send cross-domain requests on behalf of the user from my website, right? So which effectively means the attacker can now conduct compression Oracle attacks on HTTP requests and responses. Let's try and see this in a quick demo. I hope really it works, because there's some brute force involved. I was trying to test this in the Wi-Fi over here. I have a video as well, but if the demo fails, I'm going to show you the video. So, yeah. The browser is Firefox. There's a reason I couldn't use Chrome. I'll come to that a little later. And I'm using the OpenVPN client, which is the OpenVPN 3. This is from their latest GitHub source. So today, if anyone is implementing a VPN based out of OpenVPN, they are going to be using this client. And so that's like more or less like a library. So that's what I'm using, and I'm using an OpenVPN server. And I created a subdomain called insecure.skepticfx.com. It's basically just a HTTP web app, which is used for the proof of concept in this demo. As usual, the attacker's aim here is to steal the session ID from insecure.skepticfx.com. So let's try and take a look at that. Okay. So just to start, I'm going to show, I'm just connected to the hotel Wi-Fi here. So let me start the VPN. So this is the OpenVPN code that I just said I compiled locally. It's the OpenVPN 3. Now I'm trying to connect it to my OpenVPN server. I've hosted it on a cloud provider. And the important thing to notice here is the parameters that are being negotiated. So this is by default trying to connect to them, and the compression algorithm uses LZO, right? So that's good. I'll just confirming I'm just connected and everything is good. All right, so I'm just connected to this. Okay. All right. Now I'm going to this one where, yeah, I'm going to show you this demo web app. As I mentioned, it's on pure HTTP. However, this on the wire is going to be protected because of the VPN, right? It's not insecure anymore, technically. And what this web app does is generate cookies here. So when I generate these cookies, as you can see, it changes here. So for in this case, let's say this is the cookie. Now, from a same origin policy browser's point of view, this cookie cannot be stolen from another website, say localhost or attacker.com. So I'm going to start my man in the middle. So basically, this is just a KB script which runs and looks for OpenVPN connection and forwards everything to the attacker server. So in this case, that's attacker.com. So it's just sniffing for OpenVPN packets. And I'm going to start the, just a second. Yeah. I'm going to start the attacker server here, which is running locally now, but this, you can imagine this running technically on a actual web app on the internet, most preferably closer to the target client that you want to attack, because these are very precision-based attacks. It's very hard to, you can miss a few packets and things can completely screw up. your entire brute force thing will screw up. So it needs to be a little deterministic. So you try your best to make it, avoid those network issues. Let's see. So I've just hosted it on localhost 9000 for now. All right. So what this code tries to do now is try and create a WebSocket connection to its server from the client and listen to the packets that comes from this Python client, which injects it to the server. Now, let's see what happens. Hopefully it works. Okay. Okay, good. I think 3 more characters, or 2 more. Yes. All right, I think I got it. Thank you. So, hey. All right, yeah, that's the one. So what really happens here? So this is the one that tries to send it here. And as you can see from here, this is the server which tries to get the base length and try and guess each character. So in this case, when I guessed 8, what I'm doing here is sending 10 packets starting from 0, 1, 2, 3, 4. I mean, I'm brute forcing the numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8. So you can see the last but 1 packet. So this is for 9 and this is for 8. So I can take this 10 packets and observe that the 9th packet had a compression oracle, which means my 9th packet, which was number 8, was the actual character. And if you can do that deterministically for everything, you get the secret, right? So, yeah, let's get back to the talk. So, right. And I've added this code and I'll be releasing it later today. You can take a look at this at skepticfs/oracle on GitHub. It also has some code to detect your own compression oracle attacks on your own VPNs, and you can carry out this attack on almost any VPN. All you have to do is, let me show you something more. Just go and change this code. So in this case, if you can see this, yeah. So you just need to specify your target HTTP web app and your secret prefix cookie. So this is the well-known attacker-controlled part that the attacker would choose to inject. So everything that I'm going to brute force is going to be after this. So if your target web application has, let's say, a Java web app, and which has cookies, say cookie : space J session ID, then you have to just replace them here, and it should just work fine on that target client. Right? Okay. So here's where the interesting thing comes. This is a challenge I saw, which is very different from the crime-style attacks. So if you looked at the demo and the whole theory of what I've been talking about so far, it's from a high level, it's very inspired by crime-style attacks, just applied it to VPNs. However, there are a few differences when it comes to VPN, right? So when you look at any of these attacks which targets HTTPS, the attacker has a luxury in actually being more deterministic with these packets, which is he can write escape his scripts while doing an MITM in such a way that it will only look for requests which goes to the specific target web application. So in this case, let's say you're trying to attack PayPal.com, you can specifically look for TLS client handshakes, which has PayPal.com in the SNI, the server name indication field, which I hope will get encrypted very soon. I'm not so sure, but yeah. And in general, the VPN traffic is also very, very noisy. What I mean to say here is that all the traffic goes through this, right? So if you're trying to observe a client, the DNS packets are specific, the HTTP traffic is separate, the HTTPS traffic is separate, which you can further reduce down using SNI. However, when you're observing a client using a VPN, it's all going to be a mess. If I just show you the Wireshark for this, it will be just OpenVPN with no more extra information, because everything is going to the same target VPN server. So one of the things I try to do in this attack to determine the actual packet which I'm sending to, and the way I'm trying to differentiate it from the actual the different traffic that goes on the client's bots, is to do some form of classification, a very basic one, which is try and send 10 packets among the noise, and try to make sure that you can get those 10 classified in a very specific region. And if you can try and keep your compression oracle attacks or your brute force within that range, you could basically do the attack. So from a high level, all you have to do is move the length of your data that you are interested in to a very specific range, so that no other packets usually come under that range. And that has proven to be more effective. If someone is interested in working more on this or advancing, I think that would be a very interesting area to look into. Probably use some machine learning, I don't know, but it's possible to do more things there. And another interesting thing with specific to OpenVPN that I observed is that you need your browser plays a huge role here as well. I mentioned that Chrome was not vulnerable to this, partly because I was not able to conduct this attack on OpenVPN using simple GET requests. I always had to make post cross-domain requests for the compression to trigger. So in Google Chrome, if you send a HTTP packet and without any VPN, just try sending a HTTP packet, and it will always split the request headers and the request body. If you send a HTTP post, it splits them into two different HTTP application data packet. Unlike Firefox, which does the usual thing that is expected. There's nothing to complain here about the browsers. I am not so sure why Chrome does that. I'm pretty sure it's definitely not for preventing against compression oracle attacks. It has got to do something with, I believe, some performance-related stuff. I'm not so sure. So if you look at other browsers like Firefox and Safari, you get everything in the same window, so you can trigger the compression within the same HTTP packet data. All right. So detecting oracle in your own VPN. So this is more or less like if you have a provider who's using OpenVPN, it's pretty straightforward. Just go and look into your client configuration, if that's possible. If for any OpenVPN that's out there, or any implementations of it, it would usually have a client file, and in this case, you would have comp LZO enabled. And regardless of the client file, if your server disables compression, your compression doesn't work. So the best way to do it is to actually dynamically test. I haven't tested all the VPNs out there, but the ones that I've tested and have compression enabled, the attack was possible. And this is how I tested without doing a full-fledged exploit. What I did was, so here's your do-it-yourself oracle detection. All you need is a Wireshark, a terminal with curl, and you need to connect your VPN under test, and just send curl request and observe the payload length. Very simple. So if you have a custom VPN, all you have to do is send this specific, copy-paste this data for a given HTTP website, and let's say the length is X, and if you just change those twos, you should expect the length to be still X, until unless they become 3, and in which case the compression oracle would be triggered, and in which case the compression would be triggered, and you would have an oracle which is a lesser length. So this is how I tested different protocols, and the thing is, I'm not talking about all the protocols that are vulnerable to here, because I'm just more specifically talking about OpenVPN for today's talk. So yeah. Fits. So fits is something which is very interesting. Different people have different opinions about how to fix compression oracle. If you have heard about how breach works and how people are trying to defend breach, there's not a full-fledged answer to that. Breach is probably still possible in few web apps. The only thing that's a limitation is that it's due to the network issues, and it's not very reliable. It's not a precision attack where you can clearly say and it just leaks the secret. You need to be very targeted. So talking about defenses, I would like to bring in a good example of Speedy. So when the crime authors, Giuliano and Thoidong, talked about Speedy, they talked about how Speedy's header compression, which is today's HTTP2 header compression, works. It's more or less similar to that. And the way they fixed it in HTTP2 is using something known as HPAC. I believe this already started from Speedy. And the way HPAC works is by disabling sensitive information. So they have something known as the never indexed literals. So if you're going to compress something that is sensitive, like cookies or authorization headers, you just completely disable compression. And CloudFlare, they had a solution for breach-style compression oracle attacks. You can read more about this on their blog. So they have this CF no compress, which is again very specifically targeted towards breach-style attacks and how to detect them as a plugin on your server. So what they try to do is, if you have sensitive information like CSRF tokens, the compression algorithm just completely ignores. The gzip response compression completely ignores your ignores compression for that specific payload. All right. So here's my take on VPNs. So for a VPN, if you look at the percentage of traffic that is purely HTTP, it would be almost, it should be very less. So the people who are trying to use HTTP for VPN, they should definitely get away from that because that shouldn't be the use case for using a VPN. It should be to, in general, trying to, things like being anonymous and stuff like that. I believe the encryption layer should come directly from the protocol itself, like what TLS is trying to do. Like they are trying, the TLS 1.3, they're trying to even try and, there are even proposals to try and make SNI encrypted, if at all that works. There are a lot of complex reasons why that can't be done, but it's great that you're pushing for encryption right at the protocol level, just like what DNS is also trying to do with DNS over HTTPS. So in VPNs, turning off compression off by default with the vendors I've talked with is a very interesting scenario. I will just quote a couple of instances here. So with OpenVPN, they do agree, yeah, there's a problem. We should, instead of disabling it completely, they want more users that we are going to disable them by default. And they had two camps as well, OpenVPN. One camp was like okay with disabling compression by default, and only people who want it should enable it. There's a other camp which is the one that's existing right now, which is you would have compression enabled by default. So all the OpenVPNs that are out there by default would have this. And the other vendor I worked with was TunnelBear. They were interesting. It's one of my favorite SaaS VPNs. And they immediately turned off compression when I showed them a POC which leaks secrets cross-domain. So that worked out very well, and the POC was easier because it's based on OpenVPN as well. So yeah, from a high level, I believe it's time. We have been hearing this for a long time, move to HTTPS. Yes, that is there, but if you are still someone who's using specific HTTP through VPN, that VPN is not going to solve your problem. That's the high level overview from my point. And end users and website users should do that. And as a VPN provider, I would suggest that if you can have a way of disabling compression purely for non-secure protocols, that would be great. So yeah, I think I ended up a little early. I have how many? I have 10 more minutes for questions, if you have any. Thank you. Yeah. So, any questions? Yeah. Okay.
Hello. So you looked at HTTP traffic.
Yes.
But in a corporate environment, there are a lot of other protocols that transmit data over plain text, right? So would this also work if somebody is using FTP, for example?
Yes. So I think that's a good question. So what he was asking was that if are you able, I'm just repeating the question. very able to conduct this attack on other protocols as well, not just HTTP, other interesting protocols like FTP as well. So the answer to that is these style of compression Oracle attacks completely relies on the fact that you have a browser style environment. You want a way to trigger requests which injects your attacker control data and takes existing secrets along with it. Browser is something which does that entirely very well. FTP, I'm not so sure, but some of the email clients with the recent e-fail style attacks, maybe that's possible. If you, I haven't looked much into it, but I believe there is a combination which is probably possible if you use the same approach like what the e-fail guys used in PGP, but I'm not entirely sure. Yep, that's.
I asked this because FTP can also be accessed using a browser, right? And you enter username and credentials. I'm looking at if you
the authorization header.
If that's a different thing.
Oh yeah. So yeah, I haven't looked into that. Yeah, that's definitely a very interesting area to look into. That'll be bad as well. Yeah. Thank you.
Thanks.
Yep. There's a question over behind.
Hello. Hi. So I'm one of the authors of Breach.
Could you be a little loud?
Yeah, I'm one of the authors of Breach. Great work.
Hi.
Hopefully I can get you a beer after. But anyways, have you had any chance to look into HTTPS over VPN? So what I mean by that is, imagine VPN with no compression, and there's HTTPS traffic with compression on top of it. Have you looked into that? I think it might be vulnerable still, but I'm wondering.
Yeah. By the way, the guy who asked the question is one of the authors of Breach. Is it Angelo, Bravo?
Angelo, yes.
Yeah,
nice
great.
to meet you. So,
hi. So basically what they asked was, how about HTTPS with compression Oracle attacks? So from my experience of what I've looked into, I just applied the basic premises of crime here. I don't think which is a chosen plain text attack. So the moment you have HTTPS, I think your plain text is already encrypted. And I'm not so sure whether that would entirely apply here, but I think the coolest attack to have in this class of stuff is to have VPN and HTTPS and still break them. Right. And someone could do that, that'll be awesome.
I think it might be possible.
Yeah.
We should look into it. Thanks.
Thanks. We should definitely catch up after this. Yeah. All right. So, anything else? All right. Thank you. Really appreciate your time here.